Hey everyone, and welcome back to the deep dive. You know the drill. You're here because you want to understand big ideas fast, no fluff, no filler.
Straight to the good stuff.
Right. Today, we're going deep on programming fundamentals. We're talking about the core concepts behind, well, pretty much all the software you use every day.
It's like getting a peek under the hood, seeing how it all ticks.
Exactly. And to guide us through this, we're using Programming Fundamentals, Comprehensive Guide for Beginners, as our roadmap. This deep dive, our mission is to unpack the most essential building blocks of coding.
We want to make sure you understand them, even if you've never written a line of code in your life.
No jargon, just the core concepts that really matter. So before we jump into the nitty-gritty, can you give us the big picture? What exactly are programming fundamentals and why are they so crucial?
Imagine you're building a house, right? Programming fundamentals are like the foundation, the concrete, the framing.
The bed.
Exactly. You can't build a solid structure without a strong foundation. Same goes for software. These fundamentals are the concepts that every programmer, no matter what language they're using, relies on. It's knowing your ABCs before writing a novel.
Okay, that makes sense. So where do we even begin with this foundation? The guide starts with data structures. What's that all about?
So data structures are all about how we organize and store data. Imagine a library full of books, but no system, just piles everywhere.
Chaos.
Total chaos. You'd never find the book you need. Data structures provide the order. They give us different ways to arrange the books, so to speak, so we can easily find and retrieve the information we need.
Gotcha, keeping things organized. So what are some of the common ways to do that?
Well, one of the most basic data structures is an array. Think of it like a bookshelf. You have a row of slots, each holding a single item.
Like a row of books on a shelf.
Precisely. Arrays are great when you know exactly how many items you'll have and need to access them quickly based on their position. Then you have a stack.
Which makes me think of a stack of, well, anything. Like a stack of pancakes. You put one on top, then another, then another.
And when you're hungry, you grab the one on top, the last one you added. That's the core idea of a stack. Last in, first out. Like hitting the undo button, each action gets stacked and you undo them in reverse.
Last in, first out. Makes sense. Now, a queue sounds more like waiting your turn.
Absolutely. Imagine a line at a coffee shop. The first person in line gets their coffee first, then the next, and so on. First in, first out.
Right, so it's all about the order. Things arrive. Now, what about linked lists? The name suggests some kind of connection.
It does. Unlike arrays, where all the data is right next to each other, a linked list uses these things called pointers to connect the pieces.
Pointers.
Yeah, imagine a scavenger hunt, right?
Mhm.
Each clue tells you where to find the next one. In a linked list, each piece of data points to the next one in the sequence, forming a chain. This makes them super flexible for inserting or deleting items without having to move everything else around.
Ah, so it's more adaptable than an array. And then there are binary trees. I never thought I'd see trees in computer science.
Aha, no leaves here. A binary tree is like a family tree. Each node has, at most, 2 children. And this branching structure makes them incredibly efficient for searching through sorted data. Imagine looking up a word in a dictionary. You keep narrowing your search by going left or right.
Right, cutting the possibilities in half each time. Efficiency is key.
Exactly. They're also great for representing hierarchies, like folders and files on your computer. Finally, we have graphs. Think networks, connections.
Social networks, maps, that kind of thing.
Bingo! A graph consists of nodes, which could be people, cities, whatever, and edges, which are the connections between them. It's a powerful way to model relationships and dependencies.
So it's all about how things are connected. Wow, so many ways to organize data. Okay, moving on, the guide then talks about variable declaration. What's that all about?
Think of a variable as a container where you can store a piece of data, like a box you can label and put stuff in. Declaring a variable is like reserving that space in the computer's memory and giving it a name.
So it's like saying, hey, computer, I need some space to store this piece of information, and I'm going to call it score.
Exactly. And there are some rules for these names. You can use letters, numbers, underscores, but they can't start with a number, and it's always best to make the name descriptive.
Makes sense. So it's not just about having a container, but also giving it a meaningful label.
Right. And there are different types of variables. It's about where they live in the code and how they can be accessed. You've got local variables that exist only in a specific part of the code, global variables that are accessible from anywhere, and constants, which are like fixed values that never change. Then you have class variables shared by all instances of a class. Think of all the enemy characters in a game. And instance variables, which are unique to each object, like each enemy's health.
Okay, so it's about defining where the data lives and how it can be used. Now let's talk about something no one likes dealing with, debugging.
The bane of every programmer's existence. But hey, it's part of the process.
So what is it exactly?
Debugging is basically the process of finding and fixing errors in your code. The guide talks about three main types of errors you'll likely encounter.
Syntax, logical, and latent.
You got it. Syntax errors are like grammatical errors in a sentence. You've broken a rule of the programming language, and the computer doesn't understand what you're trying to do. It's like having a misspelled word. The program won't even run until you fix these.
So it's like the computer saying, wait a minute, this sentence makes no sense.
Exactly. Then you have logical errors. Here, the code might run just fine, but it doesn't produce the result you expect. It's like following a recipe, but you accidentally put in salt instead of sugar. The cake bakes, but it's not going to taste right.
A salty cake, not good.
Nope. The program might do something, but it's not doing what you intended it to do. And finally, you have latent errors. These are the sneaky ones. They hide and only show up under specific circumstances.
So it's working fine most of the time, but then, bam, a problem.
Exactly. It might be fine with normal input, but then someone enters an unexpected value and the whole thing crashes. A real headache.
So debugging is this whole process of hunting down and squashing all these different kinds of bugs. Sounds like a lot of fun.
What can be challenging, but it's also incredibly satisfying when you finally solve that tricky bug.
I bet. Now let's move on to something that sounds a bit more advanced. Object-oriented programming, or OOP. The guy says it's about organizing code around objects. Can you break that down for us?
Sure. Imagine you're building with Legos. Each Lego brick is like an object in OOP. It has properties, like its color and shape, and it can connect with other bricks in specific ways.
Okay, so it's like creating modular building blocks.
Exactly. In OOP, you create these blueprints called classes, which define what the objects are like. Let's say you have a car class. It defines what a car is, what properties it has, like color, model, speed, and what actions it can do, like accelerate or brake.
So it's like a template for creating different types of cars.
Exactly. You can then create multiple objects based on that class, each with its unique properties.
Like a red sports car, a blue truck, and a yellow minivan.
Precisely. Now, OOP relies on four core principles: inheritance, polymorphism, abstraction, and encapsulation.
Wow, those are some big words. Let's tackle them one by one. What's inheritance?
Inheritance is all about reusability. It's like saying, hey, this new object is basically like this other object, but with a few tweaks.
So instead of starting from scratch, you build on what's already there.
Exactly. Think of it like animal species. You have a general animal class, and then you can have more specific classes like dog or cat that inherit the common properties of being an animal, but also have their own unique traits.
Okay, that makes sense. What about polymorphism? That sounds like something out of a science fiction movie.
It's actually pretty simple. Polymorphism means that objects of different classes can respond to the same command in their own way.
So if you tell a dog to make a sound, it barks. But if you tell a cat to make a sound, it meows.
Exactly. Same command, different result, depending on the object. It makes your code more flexible and efficient. Now, abstraction is all about hiding the complexity.
So like how you don't need to know how a car engine works to drive it.
Exactly. Abstraction is about presenting a simplified interface to the user so they don't need to worry about all the nitty-gritty details.
Makes things easier to manage.
Absolutely. Finally, encapsulation is about bundling the data and the actions that operate on that data within the object itself.
So it's like keeping all the car parts neatly contained within the car.
Precisely. This prevents accidental modifications and keeps your code organized and manageable.
OOP sounds like a powerful way to organize complex programs, especially when you think about the guide's example of a game with different character classes.
Definitely. It promotes modularity, reusability, and maintainability. It's a game changer for software development.
Okay, we've covered data structures, variables, debugging, and OOP. The guide next talks about control structures. What are those all about?
Control structures are all about controlling the flow of execution in a program. They determine the order in which instructions are carried out.
So like traffic signals directing cars.
Precisely. You have things like if-else statements, which allow the program to make decisions based on certain conditions, and loops, which allow you to repeat a set of instructions multiple times.
Okay, so they're like the decision makers and the task repeaters in the program.
Exactly. They give your program the ability to be dynamic and responsive.
Got it. Now let's talk about basic syntax. The guide compares it to grammar in spoken language.
It's a great analogy. Syntax is the set of rules that define how you write code in a specific programming language. Just like grammar tells you how to structure a sentence, syntax tells you how to structure your code.
So things like punctuation, keywords, and the order of words matter.
Absolutely. Every programming language has its own unique syntax, and if you don't follow the rules, the computer won't be able to understand your instructions.
So it's like speaking a foreign language.
Yeah,
If you get the grammar wrong, no one will understand you.
precisely.
Okay, last but not least, the guide talks about IDEs and coding environments. Can you explain what those are?
Sure. An IDE, or Integrated Development Environment, is basically a software application that provides a comprehensive set of tools for writing and debugging code. It's like a one-stop shop for all your coding needs.
So it's like a fancy word processor, but for code.
In a way, yes. IDEs usually include a text editor for writing your code, a debugger for finding and fixing errors, and sometimes even a compiler or interpreter for translating your code into something the computer can understand.
And they usually have lots of helpful features, right? Like code completion and syntax highlighting.
Absolutely. They make your life as a programmer much easier. Now, a coding environment is a bit more general. It could be an IDE, but it could also be a more customized setup where you use different tools and configure them yourself.
So an IDE is like a pre-built house, and a coding environment is like building your own house from scratch.
That's a great way to put it.
Okay, we've covered a lot of ground here. The guide also offers some tips to improve programming skills. Mastering the fundamentals is just the beginning, right?
It is. The guide recommends a few things, like taking additional courses, especially those that include hands-on practice.
Practice makes perfect, right?
Exactly. It also encourages you to look at real-world source code, which can teach you a lot about best practices and how experienced programmers tackle problems.
Learning by example, that's smart.
Another key tip is to work on your own mini projects.
So putting what you've learned into practice.
Precisely. Building a project takes you through the whole process, from planning to execution, and it helps you see how all the pieces fit together. The guide also suggests participating in coding competitions, which can be a fun way to challenge yourself and learn from others.
And finally, it recommends following other programmers and their work to stay up to date and get inspired.
Exactly. Being part of a community is a huge part of learning to program.
Okay, so continuous learning and engagement are key. Now, let's wrap up with the big question. Why programming fundamentals matter? Why should our listeners care about all of this?
That's a great question. Well, for starters, understanding these fundamentals helps you grasp the core concepts of coding, no matter what language you choose to learn. It's the foundation that everything else builds on.
So you can't build a skyscraper without first understanding how to lay bricks.
Exactly. Second, these fundamentals equip you with valuable problem-solving skills. Programming is essentially about breaking down problems into smaller, logical steps and finding solutions.
So it's not just about writing code, it's about training your brain to think in a logical and systematic way.
Exactly. And finally, mastering these fundamentals opens doors to endless possibilities. It gives you the foundation to learn any programming language and build anything you can imagine.
It's like having the keys to the digital kingdom.
I like that. The guide even lists some popular languages like Python, Java, C++, IKISS, SQL, Ruby, and Swift as great starting points.
So it's not just about learning one language, it's about understanding the universal principles behind them all.
That's the key takeaway.
Well, this has been a fantastic deep dive into the world of programming fundamentals.
It's amazing to see how these seemingly simple concepts underpin so much of our digital world.
Absolutely. And as the guide emphasizes, the key is to keep practicing and never stop learning.
The more you learn, the more you realize there's always more to discover.
So next time you open an app or browse a website, take a moment to appreciate the intricate code that makes it all work. It might just spark a new appreciation for the power of these fundamental concepts.
And who knows, maybe it'll inspire you to start building something yourself.
That's it for this deep dive, folks. Until next time, keep exploring